The Bloom filter implementation provides a probabilistic set membership test with configurable false positive rates. The structure consists of a fixed-size bit array and k-independent hash functions. Memory consumption scales linearly with the number of elements. The false positive probability p is determined by the array size m, the number of elements n, and the count of hash functions k. The optimal number of hash functions k is derived from the ratio m divided by n multiplied by the natural logarithm of 2. This calculation minimizes the false positive rate for a given memory budget. Pre-computed values for common element counts are provided in Appendix C. When k deviates significantly from the optimal value, the false positive rate increases, sometimes substantially. Hash function selection affects both performance characteristics and distribution uniformity. The implementation supports Murmur #3, Roman 20 hash, and SIP hash variants. Murmur #3 provides adequate mixing with moderate computational cost. Roman 20 hash prioritizes throughput for scenarios where speed supersedes cryptographic properties. SIP hash offers stronger collision resistance at the expense of increased latency per hash operation. The bit array is allocated as a contiguous byte-aligned buffer in system memory. Byte alignment ensures efficient access patterns on modern CPU architectures. The array size is always rounded to the nearest power of 2 to facilitate modulo operations via bitwise AND. Memory layout remains constant throughout the filter's lifetime. The structure cannot be resized after initialization. Element insertion consists of applying all k-hash functions to the input and setting the corresponding bits to 1. If a bit position has already been set, no change occurs. Insertion is idempotent. Inserting the same element multiple times produces an identical filter state. The insertion operation completes in O of k time, where k is typically between 4 and 8. Membership testing applies the same k-hash functions to the query element and examines all k-bit positions. If any bit is 0, the element is definitely not in the set. If all bits are 1, the element is probably in the set, with probability of membership determined by the false positive rate. Query latency does not depend on the number of inserted elements. The false positive probability formula is derived as p equals 1 minus the quantity of 1 minus 1 divided by m, raised to the power of k times n. This expression assumes uniform hash distribution and independence of hash functions. Actual false positive rates may deviate slightly from theoretical values when hash functions exhibit weak distribution properties or when element values are clustered. Parameter selection begins with specification of the maximum false positive rate Pmax and the expected number of elements n. The required bit array size m is computed as -n times the natural logarithm of Pmax, divided by the square of the natural logarithm of 2. This formula ensures that the theoretical false positive rate does not exceed the specified threshold. The initialization routine accepts target FB rate, expected element count, and optional hash function preference parameters. The routine validates that target FB rate is between 0.1% and 10% inclusive. If expected element count exceeds 10 million, a warning is logged. The default hash function is Murmur #3 unless otherwise specified in the configuration object. Hash function seeding enables the creation of multiple independent Bloom filters from the same initialization parameters. Each seed value produces a distinct set of hash function outputs for identical inputs. Seeding does not improve performance of a single filter, but facilitates the construction of cascaded filter hierarchies for multi-level membership testing scenarios described in advanced usage patterns. The count estimate function returns an approximate count of inserted elements based on the proportion of set bits in the array. This estimate becomes increasingly inaccurate as the fill rate approaches saturation. When more than 80% of bits are set, the count estimate has error margins exceeding 20%. The function is provided for diagnostic and monitoring purposes only, not for deterministic use. Serialization of a Bloom filter requires writing the bit array contents to an output stream, preceded by a 4-byte header containing the array size in bits. The header format is lit-length unsigned integer. No checksum or version identifier is included in the serialized format. Deserialization reconstructs the filter state by reading the header and allocating an identically sized bit array. The collision chain length within the implementation refers to the number of bits set to 1 by successful insertions. When collision chains exceed an average length of 3 per bit, false positive rates increase beyond theoretical predictions. Monitoring collision chain statistics identifies scenarios where the configured parameters are insufficient for the observed workload characteristics. Performance degradation occurs when the filter reaches saturation, defined as when 85% of bits are set. At saturation, the false positive rate approaches 100% for any query. The implementation does not prevent element insertion past saturation. Instead, it emits a diagnostic log message when crossing the 80% threshold and updates an internal saturation counter. The clear operation resets all bits in the array to 0. Clear completes in linear time proportional to the array size. A cleared filter exhibits 0 bits set and behaves identically to a newly initialized filter with the same parameters. Clear does not deallocate memory or shrink the allocated bit array. The memory footprint remains constant. The statistics interface provides access to bit count set, which returns the number of bits currently set to 1, and queries total, which increments with each membership test. These metrics facilitate monitoring filter health and false positive rate accuracy. The metrics are reset by the clear operation. Serialization includes optional timestamp information for filters maintained across system sessions.